So Ramesh, you can carry on from here.
Okay. Hey everyone. Yeah, I'll just share my screen. So give me a couple of minutes. Uh, I am hoping that my screen is hello.
Yes, your screen is visible, Ramesh.
Okay.
Yes.
Okay. Okay. Cool. Yeah. So I'll today the agenda for today is basically I'll be introducing you guys to machine learning with TensorFlow. Um, Yeah, so when I wanted to, when I was thinking about uh, presenting on this topic, the first and primary question that the first thing off the top of my head, the first thing that came into my mind was what is machine learning, and what how is it different from whatever the classical programming approach that we are doing, and we'll so we will be starting from there itself. And you can see on my screen, so the first diagram, this particular diagram is the conventional programming. In this conventional programming, you write logic, and this logic can be in different programming languages. This is what we call code, and you give it certain data, and and based on that logic, that data will be processed in some manner, and a result will be produced. Okay. So this particular paradigm, you can say, is generally works extraordinarily well when all of the rules are exceptionally well defined. I was thinking about what example we could give for conventional programming, and the most basic, the simplest example that I could come up with was the operation of summing two things. Okay. So yes, summing is a very simple example, but there are different cases when it comes to summing, because you can sum different things, like you can sum up integers, or you can sum up floating point, decimal numbers, or you can sum up complex numbers, or you can sum up real numbers and everything. But even with all of these cases, the operation of summing is really well defined. It is extraordinarily well defined. And so going about writing an algorithm in machine learning paradigm for summing would be practically an overkill. Okay. Um, where uh, where uh, this particular case wouldn't work is, say for example, a problem which is very common in this machine learning space, and that problem is called image classification. Okay. So say for example, I am tasked with writing a program in conventional programming paradigm, about writing a program that classifies an image and says whether that is the image of a cat or not. Okay. So how would I go about writing this? And the answer to that question would be, okay, so first thing is, a cat will have a certain type of face structure. Or say, if we were to compare cats versus dogs, dogs generally tend to have long nose. Okay, you could write something like that in a conventional programming paradigm, like type of thing. But generally, so then the edge case there would be, what happens if the image, in that image, the dog's nose is covered. So then how would you write the edge case for that? So this is where the entire machine learning paradigm would be a. This is one of the best, in my opinion. This is one of the best examples that you can point to machine learning and say, okay, this particular paradigm will work for this particular problem, and say, so how that works is, so instead of us writing the logic for classifying the image of a cat as a cat, what we would do is we'd figure out we collect lots of samples of cats. Okay, so lots of images of cats, and we label them, and we input that labeled data and the result of that label into that machine learning black box. And that in and of itself and that would learn what particular features would classify, what particular features are important to classify a cat as a cat. And this is generally speaking, this is the crux of how machine learning algorithms work. Generally machine learning algorithms work well in cases where the rules or the logic is particularly cumbersome to implement. Okay, and yeah, so this is like a general. So then what would be what would a ML project look like, or what are the different steps that a project ML machine learning project would go through? And these are the steps. Okay, so the initial step is the project initiation. You would have to identify what is a problem statement. Can this particular problem statement be solved using machine learning or something like that? And then you go about doing something like a data exploration, uh, where you figure out data sets for are there any data sets available for this for solving this particular problem. You would find what are the the variable correlations that you need to do. You do data analysis, you do you figure out the outliers and things like that. Data processing is the next step of that pipeline, where you would filter, you'd um, you go about looking at that data set and figuring out outliers and filtering those outliers, or maybe in some certain cases the data sets might have wrong or incorrect data, in not relevant data, which we'll need to filter out. Model development would be the process of training the model, the architecture development, architecture implementation, and things like that. Model evaluation would be doing something like how good is your model performing. Once we've trained the entire model, you take another one common step that happens in model evaluation is this process called cross validation. Okay, and this is where you take a completely unrelated data set and test your model across that data set to make sure that your model has generalized well. Okay, and the last step of that would be a model deployment. TensorFlow has a TensorFlow Lite. I'm pretty sure that some of you might have even at least heard or even worked in this TensorFlow Lite for model deployment. Okay, and yeah, so this is the next fundamental question that came up to me when I thought maybe, yeah, I should take a talk, I should present a session on this topic. And that was, what is TensorFlow and why should we use TensorFlow? And to answer the first question, TensorFlow is a free and open source framework that is used to build, train, and deploy machine learning models. It was developed by Google in 2015. Um, uh, why we should use TensorFlow is because, see, the thing is, it is a anybody who has worked with Google, obviously, we know that Google products generally tend to have very immaculate documentation. This applies for TensorFlow also. TensorFlow has some awesome documentation, and the community support, the developer experience for that is also like really good, because a lot of people experiment with TensorFlow, prototype with TensorFlow and things like that. And so you will a problem that you will encounter, it most likely somebody else would have already encountered that and already fixed that problem. So that is also one reason why I would suggest using TensorFlow. Another major reason that you can use TensorFlow is because it's used by like really big companies like Airbnb, PayPal, and Spotify. One example of this that I when I was doing the due diligence for this session, I came across this use case of using TensorFlow in Spotify, where they recommend. Spotify has a really good recommendation system. As far as I this is my personal opinion, but Spotify has hands down one of the best recommendations for this, and that recommendation system was built using TensorFlow. So I hope that if in the future, if any of you are going forward with the machine learning project, if you do have an idea, I just believe that you would consider TensorFlow for your project. Okay. And yeah, so in this particular session I will mostly be focusing on the model development and the training part of the machine learning project pipeline. And for the demo purpose as well, I will be using Google Colab. I felt that Google Colab is like a really awesome tool as far as whenever we are prototyping development. And so I have a question for the audience. How do you think a model is trained?
Uh, Hello. I think we
Yeah.
are going lots of images or similar kind of images to the model and identify based on that uh, we are going to train our model, right? Image
Yes.
or audio samples.
Yes, exactly. Yes. So, the and this is that is what Akshay has mentioned is correct. The addition, I'll just provide a generalized answer to that question, and the answer to that question would be, so what Akshay mentioned was the case of images in particular, but this particular thing can be applied to other sorts of data as well. And I'll show you a very interesting example of how something is trained with the help of linear regression. Okay, so so these blue lines or blue crosses that you see on this, these are data points. Okay, so how that works would be, you have and these are observed values. Say you just have two random variables. It could be anything. Say for example, the age of a person and the salary that that person receives, and you could just collect that data and you would just plot it here. Okay, so what linear regression does is, it, you will be able to fit a straight line. The objective of linear regression is to fit a straight line and check if those data points lie on a particular straight line. That's why it's called linear regression. Okay. um, um, and
There is one more objective. Yeah, there is one more objective to it. Like once you pick a line, right, through a data, then you can extrapolate it to in any direction. So
yes.
suppose if your age, let's say it is age and let's say something like death rate or something like that, and then you have the a number of people dying between the age of let's say 10 and 20, and then if you fit the linear regression line inside, then you can basically extrapolate the line to let's say 5 years or 25 years or 35 years and things. So that helps
Yes.
us in prediction without actually having any data. We are able
Yes.
to generate somewhat of an accurate prediction.
Yes. Yeah. To add on to what I have said, and we'll be seeing that particular prediction part of that in my demo, and I'll show you that later. Okay, and so how do you train a model in TensorFlow? And the answer, the simple, there are certain like steps that you can follow. This is a general step, and depending on your data set and the model that you are choosing, these steps can vary, but generally speaking, the steps for training a model using TensorFlow would look something like this. You so this particular process you assumes that you have a relevant data set that you can use for this particular problem that you're trying to solve. um, so you first, to search for data sets, you can use platforms like Kaggle. They have lots and lots of data sets that you can build your models upon, train your models upon, validate and things like that. Even Kaggle has even competitions that you can enroll yourself in, which they'll provide you a data set, and you'll have to figure out what particular model represents that particular data set. Okay, and then the second step is optional. And by optional I mean that if you are selecting data sets from Kaggle, the data sets, generally speaking, the data sets will be split into training and validation sets. But if you don't have a data set available in Kaggle or in a popular data set library or something like that, you would have to split your data set manually into a training and a validation set. And the next step of this training procedure would be to use the pre-process API. And I'll go into the like full detail about how that preprocessor API works, and how it is used, like within another couple of minutes. Okay, and yeah, so the next step would be to define the model architecture and implement it. And we have two APIs, namely the models API and the layers API, to define the architecture of our model. We can also implement, we can also just take up some other model, some other big model that someone else has spent hours on training, and then replace the last few layers to do something what is called as solving a downstream task. Okay, and this particular thing is called transfer learning, and we'll be seeing that in the upcoming demo. Then the next step of training would be this is not particularly training per se. This is like a pre step, and you would have to specify what particular parameters that your training should occur in, like what optimizer should it use, or what loss function should it use, or what metric should it use uh, to such that the training goes in a positive manner and we get the best results out of training. Okay, and then the last step would be to call the model.fit method, which is where you train the data set. You'd fit the data set on your model. Okay, so this is the TensorFlow pre-processing API. So the pre-processing API is something is an API which provides like a lot of pre-processing tools. What is pre-processing, or why should we do pre-processing? Okay, why should we do pre-processing is something along the lines of, say for example, if you have 100 in a just say, let's for example, let's just imagine that I have a data set which has 1,000 images of a building. Okay, of different size, different buildings. And this data set, in this data set, the each image will be of a different shape. Like the one image will be 1080 by 1080, or another image might be another aspect ratio and things like that. Okay, so then the research standard, the industry standard is that uh, generally when you are feeding your data into the model, the data should be as much standard as possible. So data standardization and data normalization and things like that will be done by the pre-processing API. The pre-processing API has a image class, and inside of that image class there is an image data generator class. Okay, this class is really awesome for doing all sorts of data pre-processing that we can do. And the good thing about this pre-processing API is that it processes images on the fly, and they are non-destructive, meaning the original data set will not be affected because you are tweaking the data set. So you don't have to back up that data set every time you are training. And so the next thing that I would like to discuss here is the image data generator class. Okay, and this implements a lot of data augmentation strategies. Okay, so data augmentation strategies, like I previously said. So okay, why I'll just explain why data augmentation is required for a machine learning project. Okay, so let's just say you have a data set with 1,000 images of cats, and the assumption here is that in all of the images the cats are standing on the center of the image. Okay, so you train your model with it, and then when you feed the model that you have trained an image of a cat laying down, it will say this is not a cat, this is a dog. Okay, these sorts of issues will be reduced to a very large extent by data augmentation. There are loads of techniques that data augmentation techniques that are supported by image data generator, such as rotation or zoom or shearing of the image and things like that. Okay, and these can be specified, and I'll show you how these are specified when I'll show you the demo. um, and this image data augmentation also helps to solve a problem called overfitting. Okay, overfitting is in a very simple, oversimplified explanation of overfitting is something along the lines of, so you trained your model on 1,000 images of a cat. Okay, and in these 1,000 images, the model was performing well in identifying the images of the training set as cat. See, you provide another image that was not part of the training set, that image will not be properly identified or classified as a cat. That issue is called overfitting. Because the model hasn't generalized very well on what particular features represent a cat, and so it just believes that only these particular images of cats or features that were extracted from these 1,000 images of cats were the only ones that represent a cat. Okay, this is just an example, and we'll now look at the TensorFlow layers API. Okay, the layers API is the API that helps us to build our own, um, is one of the building blocks of TensorFlow, and it is used to build architectures. Okay, it has like a couple of different layers to it, like convolve 2D layer, or dense layer, or max pooling 2D layer, or things like that. Okay, and here in this particular session, I want to focus a bit more on convolution layers. Okay, so many of you might have, so the thing is, I earlier I had told you that the machine learning paradigm is where you give your input data and you give it a label, right? So the thing about models, or the thing about neural networks, is that not all neural networks perform equally well on all kinds of data. What I mean by that is, say you train a particular model on images. Okay, and then you give it an audio input, it might not work really well. So convolutional neural networks are a subcategory of neural networks that work on the principle of convolution. And those convolutions are implemented, these convolution layers are implemented using something like using this layers dot convolve 2D operator. Okay, so okay, so what is a convolution? And since this is a basis of how convolutional neural networks work, I'm just going to explain a bit about what exactly is a convolution. So what you are so as far as an image is concerned, what is an image as far as a machine or a computer is concerned, is it is just a matrix of numbers. uh, like so for example, if you have a 1080 by 1080 pixel image, okay, so this 1080 by 1080 pixel image has numbers ranging from 0 to 255, and it will have a matrix of size 1080 by 1080, and where each of those numbers will be a number ranging from 0 to 255, where 0 represents absolute black and 255 represents white. This is the case of a grayscale image. In the case of an RGB image, like a colorful image that we generally see, there will be three matrices, one for each of the red, green, and blue channels. This is how images are represented. This is how images are understood as far as machines go. Okay, and you know what are convolutions? Intuitively, what convolution does is, from this particular image, it extracts certain features. Okay, um, what are these features depends on what type of kernel you use for the convolution. So what is a kernel? A kernel is another n by n matrix. So the mx and my that you see on top here is called as a Sobel kernel. Okay, and Sobel kernels, when you apply on an image like this, you apply a Sobel these two kernels, it generates an image like this. So why and then the next obvious question would be, so why are we even doing this? Okay, and the answer to that is that, based on R&D, it was understood that feeding the left image to a neural network was much less, the efficiency was much less when giving the left image as the input of the neural network. When the right image was given as the input of the neural network, the efficiency went through the roof. Okay, so this is one of the reasons, and this is the crux of how convolutional neural networks work. um, and yeah, so convolve co conv 2D is basically a layer that performs a lot of convolutions. Okay, and the thing is, we don't know what the kernel, so the thing is, how it works intuitively, and this is a very oversimplified explanation. I know that this is not the exact industry response to this, but this is for the sake of the explanation purpose. This is a very oversimplified explanation. And so the neural network, when you are feeding it an image of a cat, it will figure out what particular kernel extracts what features that can identify a cat. When you provide it with large enough set of cats, it will generalize and figure out and realize that this particular kernel is really good at classifying this particular image as a cat. This is a very oversimplified explanation, I know, but you can try to imagine. This is something that I tell myself when I get stuck on something, and I don't really understand what the neural network is doing. This is something that I tell myself, and it brings about a little bit more of clarity. So I just want to share that with you. And how convolutions work is shown in here. Okay, so earlier I had said that an image was a matrix, right? And the values were 0 to 255. Okay, so you do a particular process in machine learning called standardization. uh, Standardization and normalization, which renders your image. So the values which range from 0 to 255 will be converted to 0 to 1. Okay, and on that standardized and normalized image, you slide a kernel, like like one you have a kernel over here. This is another kernel that you slide over, and you perform that operation and you get a convolved feature. Okay, you pass this convolved feature onto onto a fully connected layer or something like that, which does the classification for. This is how convolution works. And convolutions are defined, that this entire process, the really awesome thing about TensorFlow that I feel is that this entire process, this entire process of selecting kernels or iterating over kernels and everything like that is entirely abstracted from the person that is training, from the developer, using this just a single line of code. Okay, and that is what I feel is the really cool thing about TensorFlow. Yeah, so do you have any questions up until now? Because the next part of it is just a demo, and I'll just show you a demo of how this entire thing works. And so does anybody have any questions?
So I do have one question.
Okay,
So
sure.
it's about the age detection that you were speaking of.
Okay,
So
yeah.
how does it like when you feed the images of cat, how does the system know to detect the edges? So does it convert the image to black and white? Yeah. Does it do this? Oh, okay. It converts it
No,
into
no.
this.
Okay, so okay, I think what I explained was not clear enough. But okay, so what this does is, you take that mx, you see that mx kernel here, right? When you convolve that kernel over this particular image, you will get a your image. See, in this particular image, to identify that the person in this image is a person, or whatever the object in that image is a woman or a person, the background information, these information is practically not important, right?
Yeah. Yeah.
If
I get it. Yeah.
yeah, so you just need what are the defining features of what classifies this image into a woman class, or a person class, or a human class. Okay,
Okay.
so what convolution does is, it throws away all of the unnecessary information. And I just mentioned an example of Sobel kernel because Sobel is a very famous kernel which does edge detection. When you pass an image into when you pass a Sobel kernel, when you convolve a Sobel kernel over an image, you get the edges highlighted, and the other unrelevant, not relevant information just goes out to become black.
So
And
these
just the
kernels. Okay.
yeah,
Got
yeah,
it.
go
Got it.
ahead, go ahead then.
So these kernels, they are all like already predefined, and they are
These
very
yeah, yeah, sure.
okay. So they
Yeah,
you
these
Uh,
just have
kernels
to
are
feed them.
Yeah,
Something
go
like
ahead. Somebody was asking a question.
yes, I was saying
Akshay?
like after this process, I think the image size and dimension is also changed, right?
yes, yes.
Like
Uh,
pixel, for example, it is 250 by
Yes,
250 pixels, so it is going to be
reduced
reduced
by
after
one
this
pixel. Yes,
process.
yes, and we can
So
circumvent that process by a process called padding, where you just put 0 pixels on the top and top and left of the top left on the the edges of the image, such that you don't lose valuable information.
just to add one more point, every image operation in this world, like almost 90% of the image operations in this world, can be simplified into a convolution operation. Okay. When I say, let's say, blurring, sharpening, cropping, brightness increase, contrast increase, saturation increase, hue increase, any of these operations, what all operations you want, any of these operations can be simplified into a convolution operation. Okay. So that is where this convolution. That's why convolution was chosen as the primary filter or primary process for image processing. Okay. So the question that primarily neural networks try to address here is, what are all the convolution operations that I need to do so that the output is going to be the output set that we get is going to give us the information on whether it has a lady or not. Okay. This,
So
did
the,
everybody
those
understand?
that
Or
yeah, that particular thing that the kernel understands, how does it know that, like how do
no,
they
that is the thing. No, no. So these are all predefined kernels, but you
uh,
don't need to predefine kernels. Okay. So if you can minimize every image processing operation into a convolution, right? Then what you can do is you can just try out all the kernels, right? I can start with a 3 by 3 kernel. Let's say I start initialize everything to 0. Okay. Then I can change everything to 1. Then I can change everything to 2. Then I can change everything to 3. Like that, I can try infinitely many possibilities,
okay,
right? Till I get the
yeah,
correct answer, right?
yeah, okay,
So we don't know what the actual process is. Maybe it is like, okay, I blur the image a little bit and then apply edge reduction on top of it, and then I will get the final result. That might be the uh, you know that might be the human answer. Okay, but to a
okay,
machine, it will be, I will first convolve the image with this kernel, and then I will convolve the image with this kernel, and then the output is the one that I require.
okay, okay, got
Right?
it. Yeah,
That's
got it.
how it is. Okay.
Yes. And any other questions, or
Like
can I?
I have doubt, like for example, for images we are using convolutional. For audio, we may reduce some noises and then we will filter out the original voice. But how we are going to like chat GPT kind of thing is going to be trained?
Uh,
Any
so
idea?
uh, I will answer this on the basis of what I know. Pai, correct me if I'm wrong. But there. Okay, so you. So we have. It's just like how there is a convolved 2D layer for images, there is also recurrent neural networks, or LSTMs, or even transformers. Okay, so how ChatGPT is trained is using this technology called transformers. And so transformers, so the text that it is fed into is converted into something called as embeddings. Okay, text embeddings will be generated based on the text that it is fed. And what the transformer will do is it will try to figure out what the next embedding that might come up, and it will make a prediction, and it will evaluate against the ground truth. If it is wrong, it will use a loss function, and there will be like a gradient descent and things like that, and it will move towards that particular, it will adjust its weights and biases in such a way that it will adjust the weights and biases of the transformer unit in such a way, transformer unit or transformer layer in such a way that uh, the next time its prediction is much better than the previous prediction. I hope that answered your question, actually.
Okay.
So,
And
in summary, actually, what Ramesh meant is like convolution. There are several kinds of methodologies that we use for machine learning. Okay, one of which is convolution. Okay, so convolution has been, when we tested it, it was very good for images as well as signals. Okay, so that's why we are using it for images and signals. Okay, but there are other kinds of techniques as well. There are LSTM, RNN, so many other kinds of techniques which are good for other things. So currently, what people have discovered is that there is a technique called as transformer that can be used, and that works really good for language models. Then that's what ChatGPT uses. Okay.
Okay, understood.
Uh, okay.
So our TensorFlow is capable of doing all
Yes.
kind of
Yes.
operations.
Yes. Yes.
Okay.
Exactly.
In
Exactly.
fact, you, yeah, go ahead.
You can think, yeah, you can think of it like using fire. Okay. So the same fire I can use on a matchstick. Okay. The best thing I can do is light a cigarette or light a lamp, right? The same fire on a stove can be used for cooking, right? The same fire on a refinery can be used for like melting steel or copper and things like that, right?
Yes,
That is
yes,
how
right.
all of these techniques are. The underlying principle is just matrix multiplication or matrix, changes, but how we do it and what we do it, how, what are the process that we do it, that determines what we can do with it. So the convolution matrix operation can be used for images and signals. Transformers can be used for language models. That's how it is. But underlying, if you uh, remove everything, underneath it is just fire. Just the intensity and all of those things are actually varying. That's it.
Yeah,
Okay.
that is a really good example. Okay. So, any more questions, or can I move on to the demo? Uh, okay. Since there aren't any questions, can I move on to the demo? Is that okay?
Teja, Dhananjay, any questions? Karthik,
No, no question.
Yeah, go ahead.
Teja,
Okay.
you're awfully
So,
silent. Let's roast Ramesh a little bit more next time. Okay?
uh,
Can I ask a question? Like,
Yeah, sure, Akhil, go ahead.
yeah, I mean, you are saying about overfitting of model.
yes, yes, Adi.
So, how could we identify if a model is overfitting or just underfitting?
Okay. So, the answer to that would be what by.
No, I didn't say anything.
Okay. Okay. So the answer to that would be something along the lines of, see, you train that model, right? See, I'll show this in the demo as well. But you know y- your accuracy of the model on that training set will have a very high value. Because it has created a solution, or internally it has set up a system where it hasn't generalized on the data. It just believes that this entire data set is the absolute truth. So when you pass another image that is not part of the training data, it will go absolutely wrong. It will be like, if you say, for a classification task, for example, you train it, and when you give the training image as the input to the model, when you predict from the model what is the label of the image, it will say cat. Okay. When you give an image that is not part of the training set, it will say, oh, this is a dog.
Okay, but it is
So,
a cat actually.
but it is actually a cat, yeah. So,
Okay,
because in the validation set, your that those images, it just didn't, the training was done in such a way that it was really specified towards the data set. And
okay,
that model hasn't really generalized to the uh, actual data. And
okay,
that is one way of figuring out if your model has overfit on the data set or not.
okay.
I'm going to quote
Got that.
one good example here. Think about it like somebody in your class getting 95% mark and above. Either they are super good at learning or they have learned everything by heart. Right? If they are somebody who's learning everything by heart, then if you ask them something from outside the textbook, they're probably gonna get wrong answers. Right? If they are
Yes.
somebody who learns by understanding the topic, then their answers are going to be always slightly different because they understood it in a slightly different manner, right?
Okay. Yes.
So yeah, 95 to 100 are the people who we should be worried about in machine learning. They probably did not understand English, learned everything by heart.
Okay. Yeah. So it will be like we in practical exams we by heart the codes. I mean like the codes, and that will be like overfitting. And if we learn the logic and type the code by ourselves, then that will be an efficient way, right?
Yeah, yeah, we will have a minor compilation issue or something like that. But we will, even if the question changes a little bit, we will be able to solve it. People who come by learning by heart everything. If you even if slightly change the question, probably they are gonna give a wrong answer,
Okay.
right? Because
Yes.
they learn the program by heart, they don't understand the program, right?
Yes. 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 Yes.
So that's the same with machine learning as well.
Okay. Okay. That's the question only I'm having.
Okay, thank you, Pai. That was like a really nice, a way of putting that. Okay, I like that example. I'll keep that example in my mind the next time. Okay. Uh,
Thank you, Ramesh, for all the appreciation.
okay. So can I move on
Extended.
to the demo? Okay, so I guess since there aren't any
Sure,
any
sure.
other questions, I will be moving on to the demo. Okay. Uh,
So, just give us an introduction about collapse. If everybody wants to try it out, it will be really easy.
Yes, okay. So is everybody able to see the chat that I had put on? Like I had put a message on the chat for the to the link of the resources. Is everybody able to see that message, or is it just for me?
I didn't get it, so maybe I'll
Okay,
join
so
late, I guess.
no, I guess this I had put it before the before the this one started. Maybe that might be the reason. I'll just copy the same thing and I'll put it again, so that
Even I
it will.
cannot see Ramesh. I joined right after you.
So then okay, I understand. Okay. That one's on me. Okay, so I've put it now. So
Yeah, yeah, now I got it.
yeah, I've put the resources now. So it, you have
Yeah,
a.
share it in Click also so that
Yeah,
everybody can see that.
I'll share it on Click as well. And yeah, so Google Colab is basically like a it's a runtime that Google is providing for prototyping, building machine learning models and things like that. It's like a really awesome tool. The thing is that they provide for the free tier as well. They provide like I guess the TensorFlow runtime that I'm currently connected to is a T4 GPU. Okay, yeah. So I'm connected to a GPU instance, and you can use this for. I don't know how many of you read that article that I had shared a couple of weeks back on our this one on our dot team this one, and yeah. So you can train even like you can even fine tune chat gpt's not chat gpt large language models on this particular GPU. Okay, so I'm just mentioning that because this particular GPU is that powerful, and we can use Google Colab for training and prototyping and things like that. Okay, uh, yeah. So okay, okay. Okay, so I'll just explain to you how the code has been structured. Here it's like I'm importing the necessary packages. I'm downloading and extracting the dataset. The dataset that I am using here is a small it's a filtered, it's a smaller version of the cats and dogs dataset that is available on Kaggle. This particular dataset is very famous because uh, you know vision, there are transformer models like vision transformer, for example. Once they have performed training, they what they usually do is they perform like this is like a hello world data set. For those of you who are into coding examples, this is like a hello world data set. This is the data set that a lot of people start their data set on, and this is also the data set that people test their models on to make sure that everything is working and things like that. Okay. Yeah, so this is the data set that I'm using. Then I'm using the pre-process TensorFlow's pre-process API, and I'm using the image data generator to set up the test generator as well as the validation generator. And another thing to mention or to note here is that I am currently using the I'm currently doing a method called transfer learning or last layer updation, and I'm using the Inception v3 as the base model. Okay, Inception v3 model has been trained on thousands of classes of images, and each class has like if my memory serves me right, each class had like thousands or at least 5,000 images per class. So that Inception v3 base model is really well trained, so we can use that one here. Okay, so yeah, so I and just to okay, so I've imported all the necessary data set, all the necessary packages that we need for visualization of the model's accuracy and things like that. There is something inside TensorFlow itself called TensorBoard, which we can use. But currently, I am using Matplotlib because I am more comfortable working with Matplotlib. But if it you want a more TensorFlow oriented experience, you can go ahead and integrate TensorBoard into this Google Colab. That is absolutely fine. Okay, so uh, okay, so the thing is, this particular thing is a zip file. Okay, and the zip file will be extracted to a folder inside inside the temporary folder structure. Okay, and it will be the good thing about this particular data set is that the test and training, the train and validation sets are already separated, so we don't need to write additional code that does that particular work for us. So the the summary of that, the data, when you instantiate or initialize the data generator, the method that we use here is flow from director. Okay, so what this particular thing does is I'll show you the data set. Okay, so here it has train, and here it has cats, and this particular in a folder has like I guess 1,000 images of cats. uh, See, like cat like this. Okay, so I can just provide the directory of that particular, for if I want the for the training, I just need to provide the directory which has these two classes. Okay, and that image data generator will automatically figure out what is the label of these images and convert that label into a numerical representation to be fed to the model. These are all of these things are abstracted, and previously in the session I had mentioned about data augmentation techniques, like these are when you are instantiating the generator, you can just provide, you can just specify these as parameters, and you'll be able to, or you'll be able to all of those data augmentation and things like that will be automatically applied to the image before it is fed to the model. Okay. uh, and the next important step of training the model is, the you're defining the model architecture. Like I said previously, I am using a pre-trained model, and the model that I am using currently is the Inception v3. The good thing about the Inception v3 is that TensorFlow already has Inception v3 built in to its API. So you can just call that API, you can just download those weights, and when you're instantiating that, you can just provide the weights. Okay. He hadn't provided the weights. Uh, yeah, so now I had I've just given the I've just downloaded the weights, and I've given the weights. Oh, okay. Yeah, that one. Sorry. Yeah, here you load the weights after the model is instantiated. Sorry, and you set a couple of those. So I'll just show you a summary of how big a model like Inception v3 is. So this has, if I'm not wrong, I guess 150 layers or something like that. You will have convolution 273, and then batch normalization 3 4 batch normalization layers, and then you'll have activation layers, and all sort of those things. Okay. So here we are using in this particular case, I'm going to uh, get this pre-trained model until mixed 7, which is here. Yeah, so I'll take the first 100 layers of this particular model. Okay. Which is mixed 7. Okay, and I'll add a couple of and the reason for this is that the the top layers of the model, the input layers of the inception layer, is generally more specialized towards the data set that it was built on, and these 100 layers are more generalized. So you can take the features that these layers learned, and you can use that for transfer learning. That is the reason why I'm taking this particular layer. Okay, and I am feeding that as the input to the model that I want to define. Okay. So here I am adding basically. So here this is like a 7 by the output is a 7 by 7 pixel image, and there are 768 of those stacked, and you flatten that. Flattening is something like, here it is like there are multiple matrices, right? You flatten those multiple matrices, and you feed it into the input layer of the function that you are providing. The dense layer is a fully connected layer, and I have also added a dropout layer here. Dropout basically also helps in avoiding overfitting. Defining what is dropout is a bit beyond the scope of this session, so I'll leave that up to you guys to figure out. And yeah, so the summary you can see that after mixed 7, in that original model it had another 50 layers, but in here, so it's flattened, dense, dropout, and dense underscore. Okay. So and now I'm gonna just compile the model, and the parameter that I'll be using is binary cross entropy for loss. Since this has only two classes for the for training, we are using a binary cross entropy, and for the optimizer I'm using RMS prop. RMS prop, you can also use other automatic learning rate adjustment optimizers, such as Adam or Adagrad. Adagrad is also okay, that will also work, but I'm just using RMS prop because I found that it produces the best results. And I'll just start the training. This will take, I guess, 2 or 3 minutes to finish. uh, this is I'm just feeding it the train generator, and I'm feeding it the validation generator, and I'm running that particular thing for 10 epochs. Okay, so 10 epochs means that you're iterating over your data set 10 times. That is the basic understanding of what epochs mean. uh, so we'll wait for I just this takes around 2 minutes or so. And this takes 2 minutes because because the as you can see, as you can see here, this is just for training it is just 2000 images belonging to two classes. So each class only has like 1000 images, which is a very small data set. Okay. uh, 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 Conventionally, when you are going for a machine learning project, like a full production scale project, it might take a very large amount of time because you will have to train your model for large amounts of data. So currently it has only two classes. In a multi class classification problem, you will have tens or 20 classes, and each class would require tens of thousands of images, and that will take tons of memory as well as compute resources. um, but just to make it demoable for the demo purpose, I'm just using a very small filtered data set. Just wanted to
Uh, can I ask a
yeah,
question?
yeah, sure, go ahead, Ravi.
So what? How do you figure the ideal number of images or data sets that you provided to the model? Like, is there any way you could figure out the number of, like an efficient way to figure out like this number of images is enough, or like this variety of images and this number of variety of images is enough?
Generally speaking,
Okay.
no. I mean, like, the thing is that is one of the reasons why in machine learning practice, they say, this is something that I've heard a lot of people say about. And people generally say something like, in machine learning everything is about practice. So you asked me how much data is required for a particular task, right? So
I mean, like, is there any way to figure it
so
out? So, like,
way to figure it out. So the the first answer would be, that depends on what type of training you're doing. For example, if you're doing transfer learning, you can get away with a much smaller data set. Okay. But if you're training your model from scratch, a lot more data will be required for producing this same accuracy. To produce the accuracy of this particular level, you would require a very large data set. But figuring out the exact number would be difficult. even
okay.
even with a lot of practice, figuring out that exact number would be difficult. You can maybe get a ballpark. You say,
Okay.
I want 1000 to, if I'm doing transfer learning, I can get away with, again, this is entirely dependent on what type of model you are applying transfer learning to. But generally speaking, you can the rule of thumb is that if you are doing transfer learning, you can generally get away with working on a smaller data set.
Okay. Got it. Okay.
Okay. And yeah, so this is like the charts for the validation accuracy and training accuracy and things like that. And I think it was Akhil that asked the previous question. Akhil, I think you had asked the question of how to figure out if a model is overfitting or not, right? So
Yes.
in this particular case, these two lines, the red line represents the training accuracy, and the blue line represents the validation accuracy, right? So uh, in this particular case, overfitting is not there. But if overfitting was there, what you would see is the training accuracy would be very high. This particular red line would be high, and the validation, the blue line, validation accuracy would be somewhere around here. That particular case, you would understand that your model has not generalized properly, and your model has overfit. That is also one
Okay.
way to figure out.
Okay.
Okay. I just wanted to mention that. Okay.
Okay. Okay.
And we'll just the last step of this is that we'll just try and see if it actually works. So I got a couple of images. The one that I just fed it now is, I guess, this particular image of the cat. Okay, of the cat. This particular image of the cat. Okay, and it was able to, so pixel CVG. Yeah, so this particular image, it was able to classify that as a cat. And the same thing we can, repeat that and say, I'll just apply all three of those. My internet is very slow, guys, please excuse me. Because these images need to be uploaded, and then, so what generally happens here is these images are of different sizes, right? Like, for example, the image of the cat was, uh, image of the cat was, yeah, so this is anyways not 150 by 150. This is the, the model was trained to fit the for the target size. The input size for the model is 150 by 150, and this particular image by any standards is not 150 by 150. So you can use a load image method, which is inside this TensorFlow's utils classes, and you can, load that image, and you can convert that image into an array. You can normalize it, and you can feed it into the model.predict class, and it will, predict, or it will figure out what particular label, uh, what particular class this image belongs to, which is what I guess previously happened, and it was able to classify that the image that I had fed in was a cat, which I'll be able to show you once these get uploaded. This particular image grooming, uh, yeah, so this particular image is like really interesting, because here it's not just one image. Okay, it's not just one dog for an image, and I was actually interested in figuring out if that was a cat or a dog. See, so this, in this particular case, it classified this as a cat. So these types of edge cases, we will have to, these types of edge cases come up when we are training, and that is one of the most interesting things that I find, because this particular image, we can't, if if I this was the first time that I was seeing I was seeing a dog, or if I hadn't seen a lot of dogs, I wouldn't be able to recognize these as dogs, right? So these types of edge cases are what makes this particular
But
field very interesting.
probability, like you can see, is very low for that is cat. I think it
Yes,
is
yes, yes.
0.08.
08, yeah, yeah,
Uh,
yeah. So that is why it is, recognizing it as a cat. Yeah, so but the other two, like, rose clay is the image of a dog, I think. Yeah, that is the image of a dog. Yeah, so this particular thing it was able to recognize, even though the images that it was trained on were like really really bad images. You can see here, like this is the type of quality of image that it was trained on. Like, see, this shaky type of image was trained on, and it was still able to recognize a photo of a cat as a cat, right? So that is what makes me interested in this particular field. And yeah, so that is all for, yeah, so that is all. I've already asked the questions, so I'm going to skip that slide. And thank you for attending the session. And I'm sorry for taking a couple of minutes extra. I think I over exceeded my time limit by, I guess, 15 minutes, right?
Thanks, man. Very informative.
Thank you.
Ramesh, anybody
And
else? Any questions?
No, nothing from my side. I don't have questions.
Akhil,
Yeah,
Teja,
I would.
Karthik, anybody?
No questions.
No, nothing.
No.
Okay.
No.
Okay. Okay. Then we will hand it over to Monica. Monica, do you want to do the final sign?
Teja, are you
Yeah.
asking? Are you sure?
No, no.
Okay.
Hey Ramesh,
Yeah, yeah.
one question. So was anything running locally or was it the whole demo was in cloud?
The entire demo was in Collab, Vishnu.
So collab runs
Actually,
locally or in cloud?
Collab runs on a virtual environment in their GCP server.
Okay. Okay. Yeah. I thought I heard your fan spinning, so I was wondering what is.
No. I have another
His
40
another thing
tabs of
is
Chrome open.
so
Okay.
he's mocking our computer pro.
Yeah, I was. I
Yeah,
kept. My focus was on that. Why is this fan spinning?
no, that's not the reason
And
why.
Ramesh, what is the
Hey,
recommended ID for this? Like
PyCharm is the recommendation.
PyCharm? Okay.
Yes. In fact, PyCharm has a extension which you can use for if you're doing machine learning projects. I'll post that in the group later.
Okay, Ramesh. Okay.
Okay. Yeah, Monica, you can take it, I guess.
Yes, so okay, now if no one has any more questions, so as our session comes to end, I would like to thank Ramesh for conducting the session and sharing valuable insights. Also would like to thank all the participants for attending and for actively participating too. So yeah, about session recordings we will share with you all. So thank you again everyone. Have a good day.
Hey guys, I just want to give all of you like one more thank you. I wanted to make it like a fully demo only type of session, but I wasn't able to pick up that sort of a. I wasn't able to complete that sort of a project. Maybe in the future demos we'll see.
Okay. And our goal is to eventually put some of this information together and like do a hackathon. Divide our entire team into two sections or three teams or something, and try to come up with a small problem statement that we try to solve or something like that. Will be really exciting to work. I think the bottleneck has been main. All of us have been hearing about all of these things. We all know probably what TensorFlow is like. We have heard about what TensorFlow is, but the main problem that I feel is that many of us have not used it. So we like to, like give it a shot as a team. Maybe next time when we get together for our, like session, maybe it can be face to face, get together or something. I like to, do a hackathon and try and see, like, give everybody a hands-on on what we can do with the AI and things like that. For some of our projects are already using AI, if you guys didn't know, but already using AI, and some of us are already using pandas and things like that. So, some elements are there, but I think, all of us are, on the edge. We just need to dip our toes in. So, we'll see what we can do together. I think. Again, thanks, Ramesh, for the wonderful session. Uh, thanks, everyone.
Thank you
Okay.
guys.
Thank you
Have
guys.
a
Bye
Thank
bye.
wonderful
you.
evening. Bye.
Thanks,
Yeah,
Thank
everyone.
you
bye bye.
everyone.
Have a
Thank you,
rest of the
thank
day.
you
Thank
everyone.
you.
Thanks. Bye. Bye.